Welcome to CSC351, writing multi-threaded mobile applications. My name is Renee. In this class today, we want to talk about multi-threading and how we can use them to keep our apps responsive. Although we are going to focus on mobile applications, everything you learn today can of course also be applied to applications that you maybe write on the server or on the desktop. We start by looking at how we can utilize multiple threads in our apps. We first have to differentiate between processes and threads because often there's a bit confusion about these two terms. And then we want to have a look at how we can keep our application responsive. Let's start at the beginning. Whenever we launch an application on the mobile device, or for that matter on any device, we are creating and starting what is called a process. A process is a single instance of one application in memory. A process represents the entirety of the application. So that's all the code, all the data, all the state, and all of this is private to the process, which means no other process can access it. Most platforms, and including your mobile device, doesn't matter if that's an iPhone or an Android device, all of them allow multiple processes to be loaded into memory simultaneously. Now, since all of our applications, they want to interact with the CPU, what happens is that the CPU registers, they will be virtualized. Each process will have its own view on the hardware. And as I mentioned, by default, one process cannot access another one. Processes are completely isolated from each other. There is one restriction on most mobile devices. That is, they only allow one copy or one instance of an application to run at a time. So it is not possible to, for instance, fire up your mail application twice. So processes, they are the entirety of our app. A process does, however, not execute any code. Instead, within each process, we will have at least one running thread. Often, we will have multiple threads. A thread is a software abstraction of the CPU. That means unique stack and copy of the registers. And each thread represents a specific execution point inside our application. Unlike processes, which cannot easily communicate with each other and one process cannot reach into a second process, this is not true for threads. All the threads within our application, they have access to the same data. We could say that data is shared across all threads. Whenever you create a process by launching an application, there will be at least one thread. And we often call this first thread the main thread, or if we are in a UI-based environment, the UI thread. And then we can of course launch secondary threads, and we call them background or worker threads. And these threads then allow our application to do multiple things at the same time. So how would that work? Back in the days, all we had were single core devices. And a single core device, by definition, can only execute one single thing at a time. Still, we have the ability to create multiple threads, and we're getting the illusion of multiple things executing at the same time. How does that work? Well, the illusion is easily explained. What happens here is that the operating system, it allows us to use multiple threads, but then it's quickly switching between those threads. So each thread gets a chance to run for a while, and then the operating system will perform what is called a context switch. It will pause the currently running thread. It's going to save the current view of the CPU, of the registers, and then it's going to load a different thread's memory and register state, and it's going to resume execution where that thread left off. And if this happens fast enough, then we don't notice. We get the illusion of multiple things being executed at the same time. On multi-core devices, it's a different story though. There, the operating system can really schedule one thread per core. So if we talk about things running simultaneously, they are actually running simultaneously. There, it's not necessarily an illusion. Simple applications, they can often survive with just a single thread. However, there are really two main areas where creating multiple threads in our apps can make our application better. Can you guess what they are? Well, the number one thing is, of course, app responsiveness. So the main thread in our app, or the UI thread, is responsible for handling all the user interaction. If you tap a button, it's the main thread that's going to handle that. The main thread is also responsible for updating the user interface. And if some system event occurs, all of this is getting handled by the main thread. So if your application blocks that main thread by using it a lot, maybe you're busy calculating some complex mathematic thing, or you're trying to draw some complicated graphic, then you block that main or UI thread and it doesn't have time to do other things. And the result will be that the app is no longer responsive. So I want to avoid that. The second thing is really somehow tied to the first one. It's all about responsiveness. Secondary threads allow us to add features to our application. So we could, for instance, run like a grammar or spell checker in the background. So as we type in a text editor, it would start underlying when we have a typo. In general, we could say that using multiple threads will increase performance. It will at least improve the perceived performance. However, threads aren't for free. There's a cost in creating and scheduling them. With multi-core devices, the cost is often mitigated by really being able to run multiple things at the same time. But if you schedule more and more threads, there will be an overhead. And that overhead is the switching, the context switching from one thread to another. So as we can see here, having multiple threads can actually lead to situations where it's going to take longer to complete some work. Let's now focus a bit on the UI thread. The UI thread is the first thread that is created if you start an application on your mobile device. And then this UI thread is essentially spinning up a while loop. And that loop is just going round and round and round. And the loop is there in order to process events that occur on your device. These are events that are either user initiated and they affect the UI, or there are some system events that occur. And all these events contribute to a so-called message queue. They are stored in there. And whenever the UI thread is done with one iteration, it will go ahead and pick the next item in this message queue and it will process it. And it becomes pretty obvious in this setup that if you do some work on the UI thread that just takes forever, it cannot pick up items from this message queue. And then your app seems to be frozen, unresponsive. Let's have a look at an example. Here we are inside a button click handler. So maybe that's part of your iOS app. And in response to a button click, which we have here, this code will be run. And this gets executed on the UI thread. That's how the typical UI frameworks work. So let's analyze what is in this method now. Well, we first call get audio data from file. So that first line already in there could potentially take long. But let's focus on the second and the third line. The second and the third line, they are both CPU intensive. And doing CPU intensive work means that the CPU is not available for other things. Here we are blocking the main thread. But now getting back to the first line and, as we're talking about it, also the last line. These are particularly important to look at because these are file operations. Now the file system and the storages on our mobile devices, they are very, very fast. It's all solid state disks there. But compared to memory access, it's still super slow. And reading a large file into memory, that can take a while. So what we do here is reading a file and writing a file. This will make the UI thread wait for this operation to complete, and all the time our app is not responding. If there was an animation running on the screen, the animation would stop. Our users would not be able to perform any actions. So long story short, we should never ever execute long operations or call methods that block or wait while we are on the UI thread. We have prepared a little exercise for you. If you please open up the exercises, you'll find exercise 1 where you have a chance to explore an unresponsive app. This is an application that does a lot of work on the CPU, and I invite you to run this on a physical device, and you'll find that it's pretty unresponsive. So just have a look at the code, make yourself familiar with the problem, and when you're done, please return to the video. Now that we know how important it is to keep an app responsive and what the differences between processes and threads are, let's go ahead and create some threads. When we talk about the concept of threads, we will sooner or later hit the tasks. That's because the way that we are creating threads these days, that just involves using the tasks API. So you're going to check that out. And whenever we create something that does not block the main thread, that is kind of running in parallel to what we're already doing, we probably want to be informed when this specific operation is done. So we have to talk about how do we wait for a task to finish. And finally, we may have operations that return values back to us when they are done. So we have to figure out how can we extract these values. First of all, let's make it very clear that threading is not a concept of .NET or C#. Even if you can use threads from within C#, it does not mean that the code to actually run them is in there. Threading is something that is part of each of the operating systems that we know and love. So if we, for example, look at iOS, we find that in order to run something asynchronously, to run something on a secondary thread, we use GCD, Grand Central Dispatch. And we can call into these APIs directly from our Xamarin iOS application. We call dispatch queue default global queue .dispatch async, and we provide the code that should be run on a secondary thread. Now what about Android? Well, in Android, very different, but again, something that is provided by the operating system. There we can create a dedicated runnable class. You see how it's implementing the iRunnable interface here. And then we pass that runnable to the async task API. And it will then execute the run method without blocking the main thread. Now both of these methods are of course platform specific. So we want to look at what is available in .NET, because when we can write code that is .NET based, it will work on all of the platforms. And there's actually a lot of choices in .NET. So let's have a look at the thread object. This is a managed class that represents a native platform thread. And it has all the API that we need to create, coordinate, and monitor those threads. This is probably the most low-level thing that you can get. Up next, we have a static method that is called threadpool.queueUserWorkItem. This is a method where we can pass in a delegate, and a thread then calls the delegate to execute the code. And both of these two here, the thread and the threadpool queueUserWorkItem, they have been a part of .NET since the very beginning. And we have another one, the system.componentModel.backgroundWorker. This is a UI component, And this UI component was added in .NET 2.0. So there was the requirement that when we are creating UI-based applications, Windows-based UI applications, that they often needed to execute something in parallel to the main thread. And so they added this component. Now, because it is a UI component, you would probably not use that outside of the context of a Windows UI application. So let's focus on cross-platform code that we can use. There is, for example, delegate.beginInvoke. This is a method that is available on every delegate, and it will invoke the method assigned to the delegate on a background thread. Again, this has always been around in .NET, and you very likely will still find code that is using it. And then second, now it's getting interesting, there is the TPL, the Task Parallel Library. This is relatively new. It was introduced in .NET 4.0. And the TPL exposes a new abstraction that is called task. This is pretty much like the queueUserWorkItem method in a way that it will execute a past method on a background thread. However, we've got a lot more control over what is going on. And it's much more of an abstraction. TPL is the newest of the asynchronous APIs. And hopefully you have watched our CSC350 class. And you know that C# itself added keywords in .NET 4.5 that makes it even easier to work with the TPL. That's async and await. So let's look at this task. The task parallel library revolves around a class named task. Put simply, a task represents a unit of work that we'd like to be executed asynchronously. Think of a task as something that will be done in the future. And the task does not make any assumptions how it will complete. It may involve a thread, but that's not necessarily required. So we can use the task parallel library to queue up individual tasks. Each will be associated with a thread, and we will pass in a delegate. In .NET, we find something that is called the task scheduler. The task scheduler will take care of all the tasks that we are planning to run. And the task scheduler tries to be intelligent. It looks at the available hardware resources, and it will only create new threads when absolutely necessary. Whenever possible, it will reuse a thread that is currently available from the so-called thread pool. By the way, if you're interested, you can also create your own task scheduler. So all of these components here are customizable and pluggable. Let's pause for a moment. If you listen closely, you heard me say that a task does not make any assumptions how it will be completed. I said it could be on a thread, but doesn't have to. So a task is really just a unit of work we want to schedule to run. And a thread is a way to execute code on a CPU. That means that often threads are used to run the logic that is associated with a task, but it's not a requirement. Sometimes the work to be done will be completed synchronously, and it may never ever use another thread. Or maybe you have got a custom scheduler, and that custom scheduler is always using one single thread to run all tasks. And then there are situations where threading is simply not required. If you're using task.delay, you're able to asynchronously wait, and this does not require a thread at all. So you see, a task is not a thread is not a task. However, often threads will be used to execute tasks. You can think of a task as, I want you to execute this code asynchronously. The mapping of a task to a thread or some other way to execute the task, that depends on a variety of factors. So what if now a task really needs a thread? Let's say we have got some CPU intensive work to be done. And we know the only way to avoid blocking the UI main thread is to run it on a separate thread. How are we going to achieve that? Well, we want to take advantage of the scheduler and the thread pool. So here's how it's working. We are creating a task and we pass the task over to the scheduler. The scheduler will see, is there a thread available? If absolutely necessary, it may create a new one, but otherwise it will pull this thread from the so-called thread pool. It will execute the task delegate, and when it's finished, the thread will return back to the thread pool, and it's then ready to execute the next assigned unit of work. To run a task on a thread, we really need a two-step process. We will later learn how we can simplify that. But to understand what is going on, we'll have a look at this here. First, we must make sure that we use the correct namespace. We find all the task-related stuff in system.threading.tasks. We can then create a task via its constructor, and as a parameter, we can pass in the operation that we would like to execute. Notice how creating that task does not execute anything yet. All we say here is, we've got a task, and this is what we want it to execute. So the next step here is to call the start method. Now you may think, okay, now it's starting the long-running operation. Now it's executing it. Not actually. What start does is it's going to hand it over to the scheduler. So there's no guarantee that just because you call start that your some long operation will immediately begin to run. It could take a bit. Here's a more graphical picture of this process. Our UI thread is creating the task and calling its start method. We just heard that this is not immediately running our delegate, but instead it's going to schedule a worker thread from the thread pool to do the work on our behalf. This thread will then eventually execute our some long-running operation, and it will execute it in parallel to the UI thread. If we have multiple cores, if we have a single core system, it will switch forth and back between the two threads, and we will only have the illusion of multiple things executing at the same time. And eventually, the assigned thread will be returned back to the thread pool. If taking 2 steps to start a task seems like a lot of work, you'll be happy to know that in .NET 4.5, Microsoft introduced a single-step API that allows us to create and start tasks through the static task.run method. This is really the method that I encourage you to use. This is the recommended way of creating tasks that should be scheduled on a thread pool. The reason is that when you use task.run, behind the scenes, it's of course doing the same things that we just showed here manually, but it is configuring the task in a way that makes it best working with the new async and await keyword. So that's why task.run is really the recommended way. One important note to make here when working with background asynchronous operations is that mobile applications have a different model for the application lifetime than desktop or web applications do. In particular, most mobile operating systems, they have very strong restrictions on what is allowed to be executed while your app is not in the foreground. If you want to learn more about these restrictions and what to do to ship around them, what is possible and what not, please have a look at our classes iOS 210 and Android 210, where we discuss backgrounding for these platforms. Just so much for now. Creating a thread and running that thread will not allow you to execute anything in the background. If you're running a thread on iOS and you go back to the home screen of your iOS device, that thread will immediately stop all execution together with your entire process. As you've seen, with this task.run API, creating tasks is pretty easy. And once we have a task, there are three very common things that we probably want to do. First, we want to get some data into the task. It's nice that we can run some long-running operation, but we typically have input data. Then we want this task to run, but very likely we want to know when it's done. And then when it is done, maybe the task wants to return something to us. Maybe it has calculated a value that we need. When we have that value, we want to update the UI. So let's see how we can achieve these three goals. Let's start with the parameters. There are different approaches that you can take to pass input into a task. The first is through the task constructor. If you look at that, we find that it has got an optional object parameter that we can use. And this will then in turn be passed to your action as a parameter. The downside is that this of course requires you to use the two-step construction, where we said we really want to use the task.run approach. There is also the task.factory.startNew method. This allows you to create a task and pass in a value in one step. However, it's discouraged to use this API. This is the original API that was exposed for a single-step task creation and starting, and it was replaced by task.run in .NET 4.5. Again, the main reason for not using anything but task.run is the compatibility with async and await. So let's have a look at an alternative approach. We could have instance level fields and properties, either in a class owner or in a dedicated data class that we can then access, write to, read from. Remember, all the threads, they share the same process memory. So this would work. Here's another approach: anonymous methods and lambda expressions. This is something that I guess you have seen very often. It's a very elegant approach. It allows you to define the data in line with the logic you want to execute. If you look at what is done here, we've got this value, this string called greeting, and we're using it inside the lambda. However, the string variable itself is declared outside of the context. And what happens here is that the C# compiler will move this greeting field, this local variable, it will move this into a compiler generated class, and it's going to put it on the garbage collection heap. And once it's in a class, it can be shared between threads, and it can of course be shared between the method that starts the task and the task body itself. Okay, our task is now running. Great. It is using our parameters, it is doing some sort of background work on our behalf, all is good. And hopefully it will be done some point later. Now, how can we tell? Well, there are a couple of ways to tell. First, the most inefficient way is to use the state properties that every task object exposes. You see in there is cancelled, is completed, and is faulted. And these will tell you the final state of the task. How did it all end? That's what these can answer. If you're interested in what is currently going on with your task, you can look at the status property. This is going to tell you about the running state. Is it still running? Is it ready to run? Is it waiting to be scheduled? Things like that. So one option would be to just create a while loop and then every second or so pull these flags or periodically check them. Now, of course, that's not a great idea, because polling means that we're going to do a busy wait, and when we do a busy wait, we're going to block our main UI thread. So why would we create a second thread to begin with if we then block our main thread waiting for this second thread? So there must be something else. And if you are using auto-completion in Visual Studio and you use your task that you've just created, you start typing my task dot, you will find that there's a wait method. All right, waiting sounds like a great idea. We can wait for this task to complete. And then you run your app, and again, you'll find that, it does indeed wait, but while it's waiting, my app is again completely unresponsive. So what is going on here? Well, number one, wait just waits indefinitely for the task to finish. So if your task never finishes, there you go, you're blocked. And second, it's going to do a busy wait. So that's not a good idea either. We can do better by using an override of the wait method where we can limit the amount of time that it's going to wait. Here we say we want to wait for a maximum of 5 seconds. Better, but it's still going to block the thread that is performing this operation. So this is not very helpful. So you know where all of this is going. I mentioned it quite a few times. Async and await to the rescue. Async and await were designed specifically to coordinate asynchronous execution using tasks with our UI thread. So here's what we're going to do. We apply the async keyword on the method definition or our delegate. And then we can use the await keyword on the task to asynchronously wait. Which means we are waiting, but we're not blocking. And that's exactly what we want. What will happen is that the current method will pause forward execution, but the thread itself will continue. It will return to the caller. It will be able to continue responding to user input or whatever is necessary. And then some later point in time when the task is done, execution will continue with all the code after the await keyword. Here's another way to look at it. We have got our UI thread, which is calling perform calculations, just some method. It then starts a task, and that task, it wants to execute the method or the delegate do snipe hunt. The UI thread is calling await on the task, and that will make it return back to the caller. No more instructions will be executed in our perform calculations method. The UI thread will be able to respond to user activity, to maybe run some animation, to react to the click of a cancel button, also important. And eventually our do snipe hunt delegate will finish, the task is complete. That's when execution will be picked up in perform calculations. This happens without us having anything to do. It's going to continue exactly where it left off. If you're not familiar with async and await, I invite you to check out our CSC350 class where we cover them. I don't think these days you can write a successful mobile application without knowing about these two. Our third challenge for tasks was that we likely want to get calculated or processed results from it. Now keep in mind that our threads, they all share the same process memory space. So this means that objects allocated in one thread, maybe the UI thread, all of these objects are accessible from any other running thread. So one way to get results is to create a field or a property in a class and set its value in the running task. Sounds good? Well, this can be dangerous because maybe you have got multiple threads and they want to access the same field. We can then run into synchronization issues. So this could mean that the value is only half there, half updated. It's corrupted. If you're interested in more details about this, we talk about this in our C#352 class. So while we can do this, it's not really optimal. So ideally, we'd be able to really return a value from a task, just like we return a value from a method. And guess what? This is possible. There is a generic version of task, which is a task of type T, and T is the return type. So we can create a task of byte, and with that we say we have got something here that in the future will return a byte. And this is really the preferred approach of working with return values from tasks. We still haven't answered the question, well, if the task is returning something, how would we get to that return value? Have a look at the second image here on the screen. You'll find that the task of type T or T result has got a result property. So using this result property, we can pull out the return value. Like that, right? Here we have got a task that is supposed to return an array of byte. we do our task.run, and in order to get to the byte array, we call or we use our task's result property. Great. However, there's a caveat here. If our task has not been completed yet, then calling and accessing the result property will block. It will do a busy wait until the task has completed. Bummer. So of course, we don't want that. We need to find a way to access the result property after the task has been completed. And you already know the answer. We have already learned about it. The answer is, of course, await. And using await does not only allow us to efficiently and asynchronously wait for the task to complete, it also extracts the return value. Now, if you look at this, we don't even have to use the result property at all. Because if we await a task to complete and the task returns a value, it will wait for it to be done and it will assign the result property to the variable, in this case reversed wave data here. So this makes the programming model a lot simpler because we can now write code that seems to be synchronous, it looks synchronous, but it is really asynchronous. And of course we've got an exercise. If you think back to the first exercise, there you explored an application that was really slow, was not responsive, and the reason was that it does a lot of work that will block the UI main thread. Now please go back to this exercise and try to make the app more responsive by introducing multiple threads. And you'll see that suddenly the UI will no longer be blocked. You can pan and zoom around and it should work a lot better. When you're done, please return back to the video. Welcome back. After this exercise, you're now able to create tasks that run on multiple threads. You successfully made an application more responsive. You also learned how to start a task, wait for it, extract values. So all of this is good. But what if something goes wrong? What if our code is not perfect? What if there's an error? So we have to deal with exceptions. And it turns out that the moment we introduce tasks, this becomes a bit tricky. We're going to introduce a type that is called aggregate exception, which is extremely useful in the context of tasks. And we want to see how we can catch exceptions. You're probably aware that if an exception is thrown in your code and you don't catch it, normally the application would be terminated immediately. We all have seen this uncaught exception error. This code snippet here will throw a divide by zero exception at runtime. So this application will fail. If you run the app in a debugger, then the debugger will catch this sort of exception. It will show you where it has occurred, but you cannot recover. And if you do it in a release build, like I said, then the app will crash. So let's now take this line here that generates a divide by zero exception, and all we change is to wrap it into a task.run. That's really the only change here. Same code, still no try catch. What should happen here? Probably you're expecting this to also terminate the app. But something interesting happens. It will not. Instead, the app won't even notice that something went wrong. So what's going on here? Using task.run can magically divide by zero? No, of course not. The reason for the behavior is that if we don't handle the exception inside the task, that means we likely want to see it as the result of the task. And that means we need to communicate it somehow to the UI thread. Because if the exception is the result, the UI thread should pick up that exception and do something about it. Show an error window. And to allow this to happen, the task scheduler in the task parallel library, it will always wrap our task code in a try-catch. So that's why nothing happened. The moment we put a task.run around our divide by zero causing code, there will be an invisible try-catch. And if we don't care about it, well then it goes unnoticed. So this means that uncaught exceptions, they never really happen inside tasks. I mean, they do, but they are caught. The framework goes even one step further. When we consume the results of the task, either by accessing the result property, by using wait or the await keyboard, then the task parallel library will rethrow the captured exception on that thread. So this is really what allows us to report an error from the background code back to our main thread or whatever thread we want to use to handle the exception. So let's go back to the unhandled exception case. Let's say that you know that an exception is possibly going to happen in the method called do something bad. It is throwing a divide by zero exception. And we just learned that accessing the result property, that will rethrow the exception. So here's what we do. Just wrap a try-catch around our call to the result property, and let's catch that divide by zero exception. Guess what's going to happen? Right. It's never ever going to go into the catch. Again, it's not working exactly the way that you probably expect it to work. Because the exception that will be rethrown here is not the original divide by zero exception. Instead, what we are getting is an aggregate exception. The aggregate exception is an exception type that acts as a holder for the real exception that has occurred. It actually is a holder for multiple exceptions that may have occurred during the asynchronous operation. So if you want to catch something here, you either have to catch this aggregate exception or you have to catch the exception base class. If we catch the aggregate exception, we can figure out what went really wrong, because the aggregate exception has got an inner exceptions property. You can iterate over all the exceptions that have occurred, and one of them, that will be our divide by zero exception. Typically, the inner exceptions collection will only have one single entry. Because what are the chances that multiple exceptions occur during an asynchronous operation? So if we look at our inner exceptions, or at the very first element of these inner exceptions, in this case here, that's where we will find our divide by zero exception. I know what you're thinking now. You're saying, well, that's ugly. I don't want to do that. I just want to catch exceptions the way I've always been catching them. Once again, using async and await, our good old friends, will solve this problem. If you are using await to extract the return value from the running task and not use the result property or anything else, you can catch the original exception, because another thing that await is doing for us is to extract the very first exception that happened. It's going to take the first exception inside that aggregate exception and rethrows that. Now, of course, if multiple exceptions happen, there's no guarantee that the one that you're looking for is really the first one. So always be aware of that. So you should always catch the specific exception that you're interested in, but make sure to also catch the regular exception. Catch exception and then say, well, something that I did not expect it happened. This topic of exceptions in tasks, it has already brought up an interesting discussion, but what if we have a task that is of a fire and forget type? What does that mean? Fire and forget means it's a task that you don't want to wait for because there's simply no need for it to wait. And it doesn't return anything either. Maybe it's a spell checker and it's just supposed to run, and while it's running it should highlight some words and you don't care when it's actually over. So what if an exception occurs in this code here? What will happen? You already know the answer. We already have seen what happens if you use a task.run and you let it execute something. It will add an implicit try-catch, and you may never ever be aware of these exceptions. So if you have these unobserved tasks, your program will never know about them. It is completely unaware that something went wrong. And this is a huge issue. The fix is quite easy. Always put a try-catch around it. You should never allow an exception to bubble out of an unobserved task. You could say now, well, I don't care. If it fails, it fails. Well, it's a bug in your application. You should care. You can even program defensively for this. If you're using the default task scheduler, then you'll get a chance to get your hands on these unobserved exceptions that occurred in tasks. You can wire up a handler like shown here, subscribe to the unobserved task exception event, and then you can, well, put something in your debug console or write something into a log file. And again, you may wonder, what if I don't care? Task ends, all is good. But you should care about bugs in your application. If that is not enough of an argument for you, maybe performance is. The task has a finalizer, and that is run whenever there's an unobserved exception. So that's how the task parallel library knows that you have never seen this exception. Then waits for the garbage collector to collect the task, sees, hey, you haven't looked at the result, there's an exception, and it's going to be reported. But having a finalizer has got a cost. Having a finalizer means that it could extend the lifetime of the task together with all the objects that it's referencing. And that means you may run out of memory because of unobserved exceptions. Let's do some exceptions. The next exercise will introduce exceptions to the code that you've been working with so far. So we want our application to fail, and we want to be able to catch these exceptions and process them using the aggregate exception that we have just learned about. When you're done with the exercise, please return to the video and we'll move on. So welcome back. You have successfully caught all of the aggregate exceptions and the inner exceptions? Well done. So our last topic will be about cancellation. If you are starting operations that run in the background or in parallel to our main thread, then some situations might occur where you decide, oh, I should probably stop what is currently going on here. Or maybe it's the user that says, I don't want to wait anymore, I'm no longer interested in the results. We should give them an option to cancel. And again, .NET has something built in that we can and should really use, and that's the cancellation source and the cancellation token. So let's discuss these. If you remember, then our task had some properties, and one of them was called status. Status indicates what is currently going on with our task, and then there are these is properties where we can figure out, is it completed? Did it error? What happened? So here are the different states. The one that we are always hoping for is that our task ran to completion. Is completed will be true. This indicates that the delegate method returned normally. Exceptions that might have occurred, they were caught and handled in the task itself. All is good. The opposite, something went wrong. Some exception was thrown in a delegate, and it was caught by the task parallel library, not by our code. So in that case, the is faulted property will be true. Also, the exception property on the task will report the exception type that has occurred. And then there's the final state. This is the one that we want to look at, cancelled. This indicates that the task did not finish its work, but it's not a failure. In this instance, the isCancelled property of the task will be set to true. And we want to figure out how we can trigger this result. Let's again have a look at a diagram. Let's say we have got a method called getFlights. GetFlights is generating multiple tasks because it wants to find the cheapest flight to some destination. And every task is responsible for communicating with the web APIs of a specific airline. Here in this case, American Airlines and Delta. So we are now waiting for flight prices to return. At some point our user decides that, I'm tired of waiting, or maybe they realize that they already have the cheapest flight price, or they figure out I want to go to France instead of Hawaii. So they press the cancel button, and then our code should react. What is happening is that the UI, the click of the button, it somehow should signal the task that, hey, don't continue to run, time to stop. But the thing is, this doesn't happen automatically. We have to write code to make that happen. And therefore, we need two things. We first need a structure that is the cancellation token. And this structure has got properties that help us to figure out, has a task been canceled, or I should say, is cancellation requested? That's also what the property is called in here, because it doesn't do any cancellation automatically. And we're going to pass this token to all of our asynchronous methods. I'm pretty sure you have been to one of these restaurants where you get these devices, you order something, they hand you out this device and they say, have a seat. And when the device is beeping or vibrating, that means you're going to come and pick up your food. So you have this token, and you're not constantly staring at that token. Just from time to time you look at it. They say, now it's blinking, I'm going to go get my food. So that's how the cancellation token is working. Now you need to get these tokens from somewhere. And that's where we will need the cancellation token source. The cancellation token is a structure. This one is a class. And this class is capable of producing a cancellation token. And the cancellation token source, that's the instance that can send out the notification to all the tokens, saying that, hey, cancellation has been requested, or coming back to my example with this device, your food is ready. It is what initiates that signal. Going back to our flight example, our getFlights method would create the token source and in exchange get back a token. The token would then be passed into each of the tasks. The code in the tasks would use the token to identify when a cancellation has been requested. And if it figures, yep, time to bail out, it would stop searching for flight prices. Here's how we create such a token, and the source, of course, and how we pass it to our tasks. Notice how the cancellation token source is the class that contains this token property. And the same token is now passed to all of our tasks, not just to one, to all of them. And then if our user requests cancellation, and remember the users can do this because we keep the UI responsive, maybe we have a button click handler, then in this click handler we call our cancellation token sources cancel method. And since our tasks, they are observing the token, they should exit as soon as possible. Bonus, if we request cancellation on a task that has not been started yet, maybe because we did not call the start method or the task scheduler hasn't run it yet, then the task itself will never be scheduled or executed. It will immediately transition to the cancel state without executing any of our work. It turns out that cancellation of running tasks is an opt-in feature. There is no way for the task parallel library to know what your task is doing, what data it's touching, what resources it's currently working on. So as a result, there's really no way for the system to automatically cancel a running task, because there would be the danger of corrupting some data. And instead, it's up to us to decide when and how and whether at all we want to cancel an already started operation. The first step in this process is to get access to the cancellation token. Unfortunately, even though we pass it into the constructor or the task.run method, it's actually not made available to our task code. So your program must somehow provide access to the correct token. Many developers, they just choose to pass it in as a parameter. That's very common. But you can really use any parameter. We already talked about them earlier. Remember, we talked about fields, we talked about this object parameter. Somehow you need to get that token in there. Once we have access to the token, we are responsible for periodically checking it. Just see if it has been signaled. So again, it's not an option for us to now kick off a while loop that does nothing but look at the token, because that would prevent us from executing our actual work. But we should not completely ignore it either. So whenever there's a good chance to look at it, we should do that. So if in this example here we have a loop of 1 million iterations, it's maybe a good idea to check after each iteration. Like that. Remember, the token has got this is cancellation requested property that we can look at. And the moment our cancellation token source calls cancel, this will become true. So what now? If we look at the method signature, we'll find that do calculation has got a double value that is returned here. So somehow we are responsible for leaving this method. It will never do it automatically. But if we leave this method, we have to return something. After all, the return type is a double value. So what are we going to return in this case? Should we return -1? But what if -1 is a legal outcome of this method? How would somebody who is calling this method be able to differentiate whether -1 means the result is -1 or -1 means it has been cancelled? So you see, that's not optimal. And that's why there's another approach here, and that is to throw a task cancelled exception. This is what you would typically do, because then the caller can catch this exception. It's an expected exception, and they can react accordingly. And because it is so common to have this check, is cancellation requested? If yes, throw a task cancelled exception. There's a convenience method inside the token which is called throw if cancellation requested. You should place this line at various spots in your task logic whenever it's safe to cancel and to bail out. On the consumer side, we will then catch this task cancelled exception. Why can we catch it? Well, because we are using await. Await will extract the first exception that happens. So we don't have to deal with the aggregate exception or anything. We're going to catch the task cancelled exception and we handle it. We clean up our UI, we restart whatever is necessary. Alternatively, you can also check the is cancelled flag on the task and only consume the results if it was successful. I pretty much prefer to catch the exception and handle it in there. Exercise time. Please go back to the exercise and add cancellation support. Whenever the user clicks the restart button or is moving our fractal around, we want to stop all the tasks that are currently running and create new ones. When you're done with the exercise, you have reached the end of this class. You will then know about how to check whether a task has completed, how to successfully cancel a task, react to the cancellation token, and very importantly, how to signal such a cancellation by using the cancellation token source. We are not done. We're done with this class, but there's a lot more to discover. We learned that the task parallel library combined with async in a way that's really powerful. You can write code that is asynchronous. It makes things a lot easier. Easier to write, but it can introduce complexity. There are potential problems when using threads. And that is, what is multiple threads try to access the same resources? We'll have to handle that. If you're interested in that, please have a look at our CSC352 class. Thank you for watching, and goodbye.